So in this Snap Circuits videos, we're continuing from project PC21 from CI-73 and going all the way to project PC30, which is the fading doorbell PC. So with project PC21, it's buzzing in the dark. There it is in the book, and here it is on the board. Now I've replaced the 3-snap here with a slide switch so the circuit can be kind of turned on and off so it's not running all the time. So we have our oscillating circuit as we've seen before with our PNP and NPN transistor with our photoresistor kind of acting as a control for the frequency on it. So let me go ahead and get Cam Studio recording the scoop here. Mine. You know, we turn on our circuit. It starts off with a nice high frequency coming out of our speaker. And as we cast a shadow over our photoresistor there, of course, we're changing the frequency of it, which is being reflected in our scope over here. So we can really blacken it out. Let's look at this on the other waveform here. Let's see, how does that look on the FFT side? You can see it kind of bouncing around on our FFT there. So that's how Project PC21 works. So Project PC22 is the Trombone PC. So here with Project PC22, the Trombone PC. Here it is in the book and here it is on the board. So I've opted to replace the speaker with the motor because it doesn't change the circuit a lot on our waveform, but it does reduce the noise since it's going through the motor there. So anyway, we're using our amplifier IC to kind of create a little bit of a feedback loop in there to give us our trombone-like effect. So get the oscilloscope started recording. And it's already pre-configured with half-millisecond divisions along with our gain and everything set where we need it. So when we turn it on with our slide switch all the way to the bottom, nothing is going to happen right now because it's not cycling back. So then bring it up some. And we get our noise from the motor there, and we can see a waveform up there that kind of goes a little bit like a sinusoidal, but it's, of course, got some mixing in there because of our capacitor in line there. And of course, the waveform changes depending on our resistance here. Amplitude doesn't change much, but of course the frequency does, and because of that our wavelength is changing there. That's one end of it. Let's look at it on the FFT side. Back to that. You can see our lines very clearly there. That's pretty definitive. And then see how everything is coming up toward the left side when we bring the resistor toward the middle here. And then it starts moving out toward the right when we go to either end here. Pause this. So that's how Project PC22 works, and now we're going to look at Project PC23, which is the sound pulse oscillator PC. And here are Project PC23 sound pulse oscillator PC. There it is in the book. Here it is on our board. And it's just our oscillator circuit like we've seen before, controlled with our variable resistor. So let's get our scope going. Go in here. And power on a circuit. Now where our variable resistor is, the circuit's not oscillating yet. Bring it up some. The circuit is oscillating there, and you can sort of see the pulses on our oscilloscope, but the problem is this is one of the downsides of the oscilloscope software using a computer, is it's simply not sampling fast enough to be able to reliably pick up the low frequency pulses coming off of our circuit here because it's oscillating so slowly. If we make it oscillate faster, then we can start seeing them a little more reliably. There. So now we start to get a little bit more waveform when we get it oscillating fast enough. And of course, as we turn our variable resistor up, the faster and faster the oscillation is. And of course, the frequency goes up. Of course, then we get to a point where technically it's oscillating so fast we can't hear it. Let's switch over to our half millisecond division. See what it looks like at these higher frequencies. Yeah, so our amplitude gets higher at lower frequencies and less at higher frequencies. We're getting one pulse there. Let's see what our good old FFT has to say about this. Of course, as expected, as the frequency gets higher, those pulses go more and more to the right. And as it gets lower, they all kind of clam up toward the left. So that's how Project PC23 works. Now we're going to look at Project PC24, which is the high-pitch bell PC. So here we are, Project PC24, the high-pitch bell PC. There it is in the book, computers on the board. So again, I've opted for the motor in place of the speaker to reduce volume, but still not affect the circuit that much. So we have another little bit of oscillator circuit here with our press switch to turn the circuit on and off. And we'll see it on our oscilloscope here, so let's get that started. Got that running now, so when we press down our press switch, a couple things happen. One, our red LED lights up. We also get some glowing from our 6-volt lamp there, and we can hear the high-pitched sound emanating from our motor there. And if we look at our waveform, we can certainly see the high-pitched sound in the waveform. Go to our half millisecond division, and you can see the high pitch there, and you can see how the waveform goes up, comes down, and then has an exponential curve, and then rises back up and repeats. Now I wonder, since I'm using the motor here, if I can affect that waveform by letting the motor run a little bit. It makes a little bit of noise on the waveform, but it doesn't actually change it that much. As if this was the speaker, it would be constant. Let's see what it looks like on our FFT scale before we get too far away here. Now that's what it looks like on the FFT scale. So that is project PC24. So now we're going to look at PC25, which is Tone Generator PC. So here we are with project PC25, the Tone Generator PC. It is in the book, and here it is on our board. So it's our simple little oscillating circuit with our whistle chip feeding through our 6-volt lamp to our speaker. So I'll go ahead and get our oscilloscope going. And turn the circuit on. So we can see from our oscilloscope and from the tone there that it's a pretty constant, fairly high-pitched tone. And it changes to half millisecond division. You can see our peaks pretty clearly there. And then when we switch to FFT, now we can see that. I'll bring the gate up a little bit. So we can see from the FFT there what the signal looks like. Now we can bring this back. And now for project PC26, we're going to put our 0.02 microfarad capacitor on top of the whistle chip to lower the frequency of the circuit by making it oscillate slower. So we see that our tone is different now. It's lower in frequency, and we can see that reflected on our spectrum here on the oscilloscope. Peaks there. Let's change it to half millisecond division. And again, from where we were just previously, there were about 3 peaks or so on here, and we're averaging about 2 or so on it right now. Take our FFT up. Now we can compare this FFT to what we had in 25 there with no capacitor. Bring this back. So now with project PC27, we're going to use our 0.1 microfarad capacitor and lower the frequency even more. So now we have a fairly low tone there, again being reflected on the scope here. And look at our waveform. And with a half millisecond division, we're only averaging about 1 peak on here compared to the 2 that we had with C1 and the 3 with just the whistle chip. FFT scale again. And you see our FFT looks quite a bit different with that capacitor on there. So that's project PC27. So now we can look at PC28, which is the old style typewriter PC. So here we are with project PC28, the old style typewriter PC. There it is in the book, and here it is on our board. So we're using our amplifier IC outputting to our speaker, and then we're using our motor as we turn it, because it kind of acts like a generator to provide input to our amplifier IC, and then we'll look at the waveform on the computer. Now I will say I've already tried this circuit, and we're going to do the best we can, because the amplifier IC has an interesting effect going on here with the interference from the computer that we've seen in previous projects, and you'll see what I mean. Because when I turn it on right now, you can probably pick up some noise, and I can amplify it by bringing my hand near the motor there. That's the issue of interference for getting back through the computer here with our cable. So we'll do the best we can. So I got my oscilloscope going. You can kind of see the pulses already, but we can get around that by flicking the motor, because this is the whole point, is to look at the waveforms that we're kind of getting flicking on there from our motor, because again we're inducing a small current by flicking the motor there, and then our amplifier IC of course amplifies that output to our speaker where we can see those effects. Oops, of course it helps if the motor stays on too. So you kind of get the idea there. Let's switch over to our FFT. See if we can get any luck on that. FFT is a little better at showing the effects. That direction is a lot more noticeable. Anyway, I think you get the idea. So that's how project PC28 works, and now we're going to move on to project PC29, which is the Transistor Fading Siren PC. So here we are with project PC29, the Transistor Fading Siren PC. There it is in the book, and here's on the board. So we have our alarm IC with a Darlington transistor setup with our PNP and NPN transistor, and the NPN's being fed via our 10 microfarad capacitor, but also our press switch, which charges it up but then also directly feeds it, and that's driving our alarm IC. So we got a little bit of residual energy at the capacitor, as you heard there. Let's go ahead and it's still discharging a little bit, making funny noises. I can see a little bit on the scope. So when I press the press switch, it starts up nice and high because we just charged our capacitor. But now as that capacitor discharges, you hear the siren fade out. And when we look at our scope, both the amplitude is getting smaller and the wavelength is getting longer. And we of course can look at this at our half millisecond per division and get a little closer look at it. And again, you see the wavelength getting longer and the amplitude getting smaller and smaller. There you have that. So now let's look at getting little blurbs out of there. So let's look at our FFT and see what that looks like. See, the FFT was pretty spread out, and then as it's getting lower, it's all pushing toward the left there. As it went out. So, that's how Project PC29 works. Now, Project PC30 is the fading doorbell PC. So for that, we are going to change this out for the music IC instead. So put this in, put the music IC in instead. We got a little bit of residual energy in there. So when we press this, of course the music IC comes up nice and loud. So let me restart it. And of course this thing does not like to do that. See if I can get it to do it here properly. There you go. As you can tell, it was whimpering out there. Actually, to make this work a little better, I'm going to put the hold function on. There, that's what it needs. So now we can do this properly. Perfect. Now it looks like they're on a half millisecond division. And again, just like the alarm IC, the amplitude gets smaller and the wavelength gets longer as that capacitor discharges. So finally, let's look at it on our FFT spectrum. Let's see how that differs to our alarm IC. So we can see the peaks there, but again, everything starts bunching up toward the left as the frequency goes down. So that's Project PC30, and that concludes this set of Snap Circuits videos.